Okay, folks, are we ready to learn about things? Yes. All right, good stuff. Thanks, Michael. Anyway, so my name is James Titcumb. I've been a PHP developer since 2002, programming since before that. I'm an avid open source contributor. Do a lot of Zen framework stuff as well. And I'm a consultant engineer at Rove, who make elephants. We do also coding things as well, but yeah, we make elephants. There is an opportunity to obtain one of these at the end of the talk. So if you just came for the elephants, I'm afraid you're going to have to sit through the whole talk as well. Anyway. OK, so we are here today to learn about the abstract syntax tree and how the compiler works and things like that, right? So to understand what an abstract syntax tree is, first of all, we need to look at how the compiler works. So the PHP code is fed into a Lexer, which generates tokens. Tokens are fed into the Parser, which results in an AST. The AST is compiled by the compiler, and that generates opcodes, which are put in the op cache and then executed in a virtual machine. OK? Cool. All right, let's go in a bit more detail. All right, so the AST is new in PHP 7, right? So let's kind of dig into this process. We start off with this thing called a Lexer, right? A Lexer in PHP, the Lexer in PHP is a generated C program. It's written in C. Actually, no one really sits down and types it, because that would be boring. We actually have this definition in Zen language scanner.l. And this is the Lexer definition, which is fed into a tool called re2c. And this definition describes how these tokens are actually split out. So who's used like token get all before and things like that? A handful of you. OK, so you know roughly how this works. And token get all is the userland API to access these tokens, right? The format, if you've ever done any kind of lexing work before, is similar to Flex, which is fast lexical analyzer, which is used by HHVM, incidentally, which no longer supports PHP, but, you know, whatever. So let's have a look at this example, right? To start off with, in the angle brackets, we've got the state, which is required for these tokens to match. All of these are in scripting, so that's just like normal PHP code, right? There are other states, like, oh, I'm inside double quotes, or I'm in a here doc or an al doc, and things like that. So that kind of tells you where you are and gives you a little bit of sort of contextual information, allows you to use the same tokens in different scenarios and sort of treat them differently. So the next bit, as you've probably kind of gathered so far, is the token itself. These are very straightforward ones. You know, they're function, die, exit, and so on. So, you know, we've seen these probably. And then the bit inside the curly braces is what happens when we match that token. In all of these cases, we're just returning the token directly, not doing anything fancy. So what we do here is we return the token, and that puts it onto this thing called a token stream. Okay? And the token stream is basically the input to the next part of the process. So the state in the angle brackets at the start allows you to use the same tokens, as I said, sort of depending on different expectations and so on. This is a slightly more complex example here. So let's look through it bit by bit. And these actually kind of pair up together. So assuming we're inside double quotes, you know, string, inside backticks, or inside here doc, we're looking for the string $, open curly brace, right? We've seen that as putting a variable inside a string. And if that happens, we want to change the state. So we're going to change the state to looking for a variable name. And then we return the token. The second part is the sort of the other side of that, right? We're currently in the looking for a variable name state. So we're like expecting a certain string. And we're looking for a label that's kind of a shorthand definition, followed by a curly brace, right? That makes sense. And then we change the state back into scripting, right? This thing here is copying the value that is the name of the variable, basically. We change back into the scripting state, and we return the variable, we return the variable name token and say this is a variable name. And so we've copied that value of that matched token as the variable name. So we've got a bit of metadata, if you like, around that. So given that syntax definition, we feed that into this re2c Lexer generator program. And this generates this C program, right? You can do that yourself. The command, if you can remember it or type as quickly as I speak, is like re2c --no --generation date --, anyway, it's a load of parameters. You can look it up probably. And you can generate the C program. It doesn't really do much by itself, but it's designed to be used by the engine to do the lexing part of the process. It's around 8,000 lines of pretty much utter nonsense, even to C developers. So, yeah, it's generated. It doesn't matter. The parser is the next part of the process, right? It actually works in a very similar way, right? We have this definition. We have Zend language parser.y. So a slightly different letter there. And this is our parser definition. So this starts getting a little bit more complicated, but real languages are complicated. And not just coding languages, programming languages, rather, coding, programming. But also real languages are complicated. English, German, Dutch, whatever languages you may speak, they're complicated things, right? And the things that a compiler does to figure out what code you've written, we also do on our heads when we're listening to each other, right? And if you're German, you may be sort of in your head just translating what I'm saying into German. You may not be. You may understand English well enough that you don't have to do that, which is great. But you're still sort of breaking up the words that I'm saying one by one, right? And that's you getting the tokens, right? Similar kind of process. And so the next part of the process is the parser. And that's making sense of the tokens that have come in what order they're in, and putting them into a bit of context, right? I can just throw loads of words at you, like chair, stage, speaker, and there's no context. It doesn't mean anything, right? And the parsing part of the process is to try and put sense behind these. And when I make a grammatically correct sentence, which very occasionally I might do, you'll be able to understand what I'm saying. So this part of the definition is basically describing an if statement. We have two definitions here. We have if statement and if statement without else. And that's basically what comprises an if statement. I've not added the definition for an expression or a statement because they're huge and can't fit on the slide without making it completely unreadable, more so than it probably already is. So we'll look at the if statement first, because, a good place to start is the beginning. And this basically says, I will match this grammar if it is an if statement without else on its own. There's this precedence thing, we can kind of ignore that. And then we go on to also match, or alternatively match, I should say, an if statement without else, followed by an else token, like the word else, right, followed by a statement. And so that's the definition of an if statement. But, as you've noticed, there's kind of stuff missing here, right? We have to find out what an if statement without else is, so we need to look at its definition. And you can see there's a bit of recursion going on here, and that's exactly how parsers work. They're usually written in a recursive way, because otherwise you'd have to define everything over and over again, which wouldn't make any sense. So we use these as like labels and embed them, so you can make a big old grammar out of just this stuff. So an if statement without else can be the word if, the if token,
followed by the literal open parentheses, followed by the whatever the definition of an expression is. Again, I've not put that onto the slide because it's big. Followed by the literal close parenthesis, followed by a statement. And again, the definition's not there. Now, it's worth kind of adding that a statement actually includes curly braces. So, I think many people these days, I know it's optional, but many people these days put curly braces in their if statements, if parentheses with an expression in, and curly brace, and then a statement. So that's actually in the statement definition, so we don't have to define it here. Alternatively, it could be an if statement without else, followed by an else if. There we go, that's the rest of it. Followed by a literal open parentheses, God, it's hard to say this stuff. Followed by an expression, close parentheses, followed by a statement, okay? So when we combine all these together, it allows us to write if, and else blocks in varying combinations, right? However you want to do it. And we're using the fact that it's recursive and we can descend and parse it in different ways and so on to our advantage. So let's try and use these rules to parse this fairly straightforward if, else block. So the first one is matched by if, the first block, if you like, is matched by if statement without else. Because it matches the definition. It's got an if, open parentheses, expression, close parentheses, and a statement, okay? Next one is matched by if statement without else, but slightly differently because we've matched inside, we've matched an if statement without else, followed by an else if token, and then an open parentheses, with an expression and a statement, okay? And then finally, the red block highlights the fact that we matched an if statement because it matches the second grammar for the if statement. That is an if statement without else, the B variety, if you like, followed by an else token, followed by a statement, okay? So we've constructed that grammar and we've understood what the code is trying to do. So, quickly going back to the definition. Notice there's these curly braces. That's basically the same thing as the Lexer, right? What do we do when we match this particular grammar? But there's something very important here. From PHP 7, the output from the parser is the abstract syntax tree. Hey, there we go. We've come full circle. If we look back at PHP 5.6, the grammar is slightly different, but this is, trust me, this is the same thing, right? You'll see that what happens when we match that grammar is we call this function zend_do_if_cond. Okay, good naming. And inside this function, we can see that we're actually creating opcodes directly. And that's how PHP used to work. It just spits out opcodes directly. So the AST is new in PHP 7. All right, now instead we're generating this thing, an AST. But, and that's kind of part of the process there. So the AST is new in PHP 7. We feed that into the compiler. That generates the opcodes eventually, which gets executed on the virtual machine. That's not like Vagrant or anything like that. It's a virtual machine because it's not actually running directly on the CPU like you might with assembly and things like that. It's a virtual machine. So let's simplify, because I haven't really said what is an AST. Okay, so let's do that now. Abstract syntax tree is just a data structure. Really, that's all there is to it. It's a representation of some code using, it's not specific to PHP, it's just a tree structure, hence the name abstract syntax tree. See how that works? It's pretty smart, I think. It's a data structure, and therefore it can be modified. And when you modify things, it modifies the behavior of your code, right? Potentially. There's also metadata attached to it, like what file and what line and column and things like that this particular piece of code is from. And an abstract syntax tree can also be unparsed. That is to say, turn it back into code from its representation, tree representation. The layout may change. Maybe we don't have enough metadata to figure out, oh, is there a space in between the if and the bracket and things like that. It's not really important to representing what the code means. So an example script. I think, unless you've never done programming, we can probably figure out what this does. We're writing out hello world, OK? So this might be a representation of that statement, but as an abstract syntax tree, drawn spectacularly well with some kind of ASCII art thing. We can see here that the echo statement is at the top, and then it has like this child node, OK? The child is a scalar string. The value is hello world, all right? So fairly straightforward. So let's make things a little bit more complicated. We put a concatenation in. If you're maybe just normally a JavaScript developer, hey, in PHP, this is how we concatenate things, not with pluses, because differences. I expect most of you have done PHP. You're at a PHP conference, so anyway. So this is what the abstract syntax tree might look like. There's a little bit more going on here. So the top node is still the echo statement, but we have this new thing as the child called concat, right? Concatenation. So this has an interesting property. It's what's known as a binary operator. That means it has a left and a right side. Okay? So the left side is the scalar string hello space, and the right side is world. Okay? That's the left and the right. Order does matter, because if you concatenate them in the wrong order, it's going to say world hello, which that's not what we're after. So the order does matter. That's why they're left and right, and not just A and B or 1 and 2, I don't know, whatever. So let's do a bit more with our code, right? We're going to assign some variables. A is 5, B is 3, and we're going to do a sum, A plus B times 2, okay? With brackets, of course. So the tree is a bit bigger now, right? You might not be able to read it, because it's kind of quite big. For this pretty straightforward bit of code, I think, already we've started getting quite large. So we've got our 2 assignment statements, all right? So we're assigning variables there. That's fairly clear what's going on, I think. We've got the type, they're integers. It's a value of 3 and things like that. And we've got our echo statement. We have an add operation. Again, that's another binary operator. You add 2 numbers together. What about when you want to add 3 numbers together? Ooh. Well, you just nest them inside each other. So an example here, well, we want to multiply something as well. So the child node is that multiply operator. So the left is the variable b, and the right is the scalar integer 2. So why? Well, why this AST thing? What's the big deal about it? And for most of the part, it's kind of about the engine itself and PHP, the engine rather than userland code, but there's more about that in a bit. But the big advantage for the engine is that it decouples the parser from the compiler. They're 2 now very distinct steps. We're not compiling, parsing and compiling as we go along, which means it's more maintainable. We've got better code quality. Code quality is good, right? And we can actually do slightly simplified productions in the parser. And in fact, the grammar, as I kind of pointed out earlier in PHP 5.6, whatever version it was, the grammar was different because it's changed and it's actually made it simpler. So it's also faster, asterisk, right? I have to say asterisk because I don't want you all to be thinking, oh, PHP 7 is faster because AST, which is not strictly true. I'll explain what I mean. Despite the extra step, there is evidence that the runtime performance doesn't really change, but the compilation step is what's faster. Now, because we have the op cache, and that's been baked into PHP since a while, I don't know, can't even remember now, the op cache is what actually makes it faster, so we don't have to keep reparsing the file every time, right? So the compilation performance doesn't really matter, right? Especially if you're deploying and warming up your op cache without, statically when you deploy and things like that. various tricks to sort of make PHP faster. The AST implementation instead is 10 to 15% faster in that compilation step, but it actually requires more memory. Why does it require more memory? Well, because we're forming this huge data structure, right? And it does get pretty big. But the real reasons why PHP 7 is faster, if you don't know, is things like the zval is much more efficient. That's like how we store variables under the engine and things like that. So it's not strictly just the AST. But what is nice, and the reason why it is faster, is that particular step. Is because these data structures, the tree, is very efficient for a compiler to traverse and look around. And we can then also look into doing performance optimization statically as well. There's not many static performance optimizations. They're actually mostly already done when we're looking at opcache, the opcodes directly, rather. So this is the same AST as we were looking at with the math sums. And I've drawn it as a tree because, well, that's what it is. It's a tree, right? So we've got exactly the same information here, but we've just drawn it out as a graph. And you can see where the name abstract syntax tree comes from. But when we show it as a tree, something interesting happens. All right? We can start walking around. And if we start at the top, follow a line all the way around, and as we go through, we can execute each node that we touch in order and descend through the tree. So we can start at the top, go left, descend down, and so on. This is called pre-order traversal. All right? This is the first time we come to a node, we always execute it. There's another one which we'll come to in a bit. And this is also known as Polish notation, right? So if you write down each of those nodes as you traverse it, this is what you end up with. And hey, you know what? This kind of actually looks like code, right? Funny that. That's what we're trying to do. But the important thing about Polish notation, or having generated it using pre-order traversal, is that the operation or the statement is prefixed, right? It comes first. And the arguments come after. And we're used to looking at that, right? That's how we normally write code. But this also has another nice benefit, and that is we can see the order of precedence, right? That's the order in which things are executed, right? Order of precedence when writing a programming language is immensely important. In fact, doing any kind of mathematics as well, order of precedence is also important. And funnily enough, programming languages actually come from mathematics, right? That's the source of it. We're doing calculations, just lots of ones and zeros these days, right? So the order of precedence is important. Well, why? Because if you write the sum 1 plus 2 times 3, if we don't know which things to do first, we're going to get different results, aren't we? Yeah? Is it 7? That's when the multiply operator has higher precedence. It gets executed first. Or is it 9, where the add comes first, right? Who knows? Well, thankfully, someone sort of decided on some rules, and you get a consistent result. And we know that if we write it out using Polish notation, it's not quite as sort of understandable, perhaps, but this actually now tells us which order we should be executing things in, all right? And so when we know this order, the result becomes obvious, right? We know the add operator takes 2 operands, left and a right, 1, and oh, there's another operator. So it's the result of that operator is what we're going to operate on. So yes, we got the operator first. The left operand is the number 1. The right operand is another operator. And so again, we kind of figure out in there. We do that first in order to get the result, pass it back to the previous operator, so we know it's 7. Okay? Make sense so far? Anyone not confused? That was an intentional double negative. Totally intentional. That was sarcasm, by the way. Anyway, reverse Polish notation is the other way around, okay? But it's not strictly just reversing the string. It's similar, but this writing it out in this different way allows us to do something called stack compilation, right? So when we're writing out in reverse Polish notation, the values come first, right? And the operand operates on the two values in the stack. And in order to build this kind of notation, we have to visit the leaf nodes first, right? Always come back, and then add everything else as we come back in the graph. And funnily enough, as you may have already guessed, this is called Postorder Traversal, okay? So that's a slightly different way of looking at it. So let's try and execute this with a slideshow stack compiler. It's not a real thing, but hey. So we're going to step through each item one by one, left to right. And if it's an operator, we're going to execute. And if it's a value, we're going to put it on the stack, okay? So the stack on the right-hand side there for you. The first item is a value, so we put it on the stack. The second item is a value, so we put it on the stack. The third item is a value, so we put it on the stack, okay? So the next one is an operator, right? It's a binary operator, so we know it takes two things. So we're going to take two things off of the stack, right? And that's our 2 and a 3. And we perform the operation. In this case, it's multiply, so we're going to get 6. And we put the result of the operation back onto the stack, right? So we put a 6 back on the stack. The next step is another operator, right? It's the add operator. We need two things. So it takes two things off of the stack. It will add them together, and we get 7. So we've reached the end of the input now, which is good, right? If the final result that you see in the stack, if your stack has more than one thing, or maybe nothing, then something's broken, okay? So you always have to end up with one thing per expression. So we are now armed with some very dangerous knowledge in which we can write our own compiler now, because that's what everyone wants to do, right? And since we're at a PHP conference and this is a PHP-centric talk, we're going to write a compiler in PHP, because why not? Don't use this in production, though. Please. And this is just for educational purposes, right? And in fact, if you like following along and exploring code, you can have a look at my GitHub. And all the source code for this is also up there as well if you prefer following along on your laptops. Or your phones, if you like browsing GitHub on your phone, perhaps. Or any kind of other kind of tablet, whatever. It's up to you what device you use. I'm not going to force that choice on you, all right? Okay. All right, so everyone got the URL? I'm just waffling a bit, so if anyone wants the URL. Anyone still want the URL? No? No? Okay, good. Right, fine. Let's carry on. So first up, we need to define our language. We need to know what it's going to look like, all right? Our language for today is just going to be very basic sums, okay? Add, subtract, multiply, and divide, all right? The basicest sums, right? We're going to allow white space in our language, but we're going to ignore it. And we're only going to use positive whole integers as values, right? So no decimals, no negative numbers are allowed, anything like that. It's a very restrictive language, but for good reason, because otherwise we can't write a compiler in like 20 minutes. So there's just the 4 operators, and also we only support one line of input. You can't do more than one sum. So altogether, not really that useful in production anyway. And another key thing, I'm going to say that there's no way to override the order of precedence. And the reason why is because it gets very complicated very quickly, and I'm just showing you the basics here, right? Step 1 is to write a Lexer. Well, we've got these tokens, right? They're pretty straightforward. So we can use regular expressions, right? That's one way of writing a Lexer, because we're just matching stuff, right? That makes sense? Yeah? Note that all of the regular expressions here, if you are terrified of regular expressions, I'm sorry if you're sweating in your chairs right now. No, not these regular expressions. I'll just draw your attention to they all start with the circumflex character. And that means, if you don't know, that we're anchoring to the start of the string. All right? So we're always looking at the start of the string, do we match this token? All right? And you'll see why shortly. So this is basically, this is the first half of the Lexer. It's really that short. basically, we're going to step through the string bit by bit, and we're going to analyze from our offset, which we're going to increase each time, in order to step through it and match things bit by bit. So each time we match something, we're going to move the offset on by the length of the lexeme. Now, the lexeme is just a fancy word for the thing what we just matched. That was really good English. The thing that we just matched. And that's the lexeme, right? The lexeme is useful information, so we want to know about it, right? And so this is used here when we do our actual matching. And the actual match is just looping over the regular expressions, and that's pretty much it. Seeing if they match. If they match, then we give it the lexeme, and we create this object. You can use arrays, it doesn't really matter. I used objects because. And that's it. And you'll notice at the bottom, if we don't match anything, hey, this is a syntax error, basically. Right? We've found something we didn't expect. All right? And so that's how we detect syntax errors. So yeah, that's it. That's the Lexer, done. So we've just got this array with lots and lots of tokens. And we can feed that into the next step, the parser. So let's parse these tokens, right? But we need to, first of all, define our order of precedence. That's important. So we're going to use standard operator precedence here, not do anything fancy or unexpected. Of course, if you change things around, you'll change the order in which things happen and maybe get unexpected results. But maybe in your language, that's fine. I don't know, maybe it's unexpected rubbish math sum compiler thing. So in this case, multiply is the highest precedence, has the biggest number, and subtract is the lowest. That's standard mathematical rules. Okay, so first up, we need to order the tokens by order of precedence. So we're going to loop over the tokens that we've done using two stacks. An output stack and an operator stack, which is kind of temporarily used whilst we're doing this process. Everything should end up on the output stack, as the name suggests. All right, so we'll have a look at how we deal with the operators and sort of descend into the code here. There's quite a lot going on here, but basically, each operator token is pushed onto the operator stack. Yeah, makes sense. However, on each iteration, we have to loop through the operator stack from the end, going backwards. And if we find something with a higher precedence, it's usually going to be the first thing if it has a higher precedence, then we're actually going to pop it from the operator stack and push it onto the output stack. Okay? And finally, any operators that are left hanging around in the operator stack, we pop them off and put them onto the output stack. Okay? And then we return the stack. So let's kind of look at this a different way to try and sort of maybe visualize this better. We're going to sequentially loop through this again, and we're going to watch the stack as we move through this process. So the first is a value, so we're going to put that straight onto the output stack. The next is an operator, right? It's an add. Now, before we do this, we check the operator stack if there's anything already of higher precedence. There's nothing in there, so the answer is no. So we put it straight onto the operator stack. The next one is a value. So nothing special there. We put it onto the output stack. And the next one, again, is an operator. It's the multiply operator. It's got a higher operator precedence than plus, so there's nothing to remove from the operator stack here. So we just add it onto the end. And finally, the last one is a value, right? And then the next step, well, we've reached the end of the input, but we've got these two operators left lying around, so we're going to take them off and put them onto our output stack. All right, so you end up with something very familiar. This is our reverse Polish notation. Isn't that great? Yeah, James, sure. So we've reordered the tokens, basically, into something that makes sense to us. Because now we can actually go through this and create our abstract syntax tree. Woo! And so we can use this stack compiler pattern that we kind of talked about to create this abstract syntax tree. So we progress through it. That's just loop, yeah. And we've got this thing called IP, instruction pointer, which for our demo is really not very useful, but if you're writing a real programming language, an instruction pointer is very important because that allows you to go backwards and forwards and so on. called read behinds and read aheads and things like that. And that allows you to do your operator precedence. There's various approaches, but again, I can't fit it all into this talk. So the instruction pointer defines where we are in the stack. We can move that around. So we're going to create the AST. If it's a value, and we only have one kind of value, it's an integer, it's always positive, and there's no decimals, so that's easy. There's only one kind of value, an integer. So we create this node. Again, the node can be an array. I've decided to use objects. It can be any kind of data structure you like, right? So the node structure should have all the metadata that you care about, right? That might be the file number, file line number, whatever. In this case, I don't care. It's always line 1, and there's always only ever one file, so there's no useful metadata there. Except we need to know what the lexeme is, the thing that we matched, right? Because we want to know what the value of the number is that we've just parsed. If it's an operator, we have to figure something out, right? We have to pop the last two values from the stack and push them onto into the operator node, right? And that's how we form the operator node. So we get those two last values, and we create a node and say this is our left and our right value. Now, the left and the right value aren't always going to be like an integer or anything like that. It can be other operators, and that's, it's a tree, right? We're allowed to do that. And there we have it, right? It will look something like this. We have our abstract syntax tree with all the nodes we expect. That's good, all right? So the next part of the process is executing that abstract syntax tree, right? So this is also quite straightforward, I think. We're going to create a tiny virtual machine, essentially, which does does the execution. So what this will do is descend around the abstract syntax tree and execute the source code. Yeah, makes sense. So this is our main compile node function. If it's a binary operator, we're going to call another function, which we'll look at in just a moment. If it's one of our scalar integer values, then we're just going to return the value of the node. Right? That's looking back. That's the lexeme we matched, and we put that into the integer value node, and that gives us the value. So that's going to be 2 or 3 or whatever the number is. We don't have any other kinds of nodes, so that's it. If we wanted to deal with white space, it doesn't matter. We just ignore white space anyway. And this is our compile the binary operator function. So an interesting aspect about this is that we don't know the type of left and right yet. So we have to actually compile those nodes. So we pass that node into our compile node function, right? So we get the left and we get the right. We pass it into compile node. And yeah, it's recursive, right? Because we don't know whether that's another binary operator that needs to be executed, or it might be just a value, in which case we just get the value back. Yeah? So when we've compiled the left and right, we need to figure out what kind of node it is. I've kind of skipped that out to make the slide fit on. But if it's an add, we do an add, funnily enough. If it's subtract, then we're going to do subtract, and so on. And you could really confuse people by changing what this actually does. Fun. Yes, but yeah, this is all PHP does. When you do like $A plus $B, it's doing that. It's just a little bit of C code that does plus or minus and things like that. That's how a virtual machine works. And of course, that is a C program in itself. And underneath that, it'd be compiled, and that runs on an actual CPU rather than a virtual CPU, right? Okay, great. What does this mean for me, or you, rather? On the surface, many people have said, well, this doesn't seem very relevant to me. Well, it kind of does. It is kind of relevant. You get faster, more efficient code that you're running your code on. AST is one of the reasons that PHP 7, or at least the compilation step of PHP 7 is faster. And there's more scope for optimizations here, right? Abstract syntax trees are not specific to PHP. And so there's a lot of well-known optimization techniques. Funnily enough, most of it has already been done just further down the process. So there's not much scope there, but there is some. All right? We can statically collapse nodes, for example. Right? If you have if you've written the number 3 in your code, then and you do a plus and then a 2, we always know that that's always going to be 5. My maths is right, yeah. Hopefully. But the compiler knows that and says, well, I don't have to always do this plus every time. I can just collapse that down and put the value 5 instead of that sum. All right? So that's that sort of static optimization there, which is kind of nice. Also, knowing how the engine works is kind of useful. And I would caveat this with saying, don't go and try and write your code like to do super tiny micro optimizations, because really it doesn't matter. PHP is very good at running rubbish code. So you can throw a lot of stuff at it that's utter nonsense, and it just kind of works. And it works quite fast these days, especially after PHP 7 came around. And it's getting slightly faster each time. And maybe there's scope for more optimizations in the future. But as I said, it's not specific to PHP. Like, the concept of having an abstract syntax tree isn't specific to PHP. Most languages already had one, because they were written by people who knew what they were doing. Rasmus isn't here, is he? No, honestly, he knows what he's doing. That's unfair of me to say, but the purpose of PHP was never to be like this big, nice language that everyone's using. If you know the history of PHP, you know this, right? It was designed to be just a form interpreter. So there wasn't this thing like, oh, I'm writing a programming language. I need to set the order of precedence, and I need to create an abstract syntax tree. It was a tool. It was getting the job done, right? So that's why it was not introduced at the very start, anyway. But all the other languages have these, or most of the other languages at least, that work in a similar way, right? These languages like JavaScript, Java, C#, things like that, they all have this abstract syntax tree step in their compilation process, because it's an efficient way of doing it. And once you understand that these all work in the same way, they all produce this abstract syntax tree, then you realize actually pretty much all programming languages are the same, or at least this kind of programming language. There are, of course, exceptions in different languages that make no sense. Name any one of them, like Haskell and things like that. They all work slightly differently, actually. But languages like JavaScript, Java, they're easy to pick up, because we already know PHP, so, JavaScript context switch, all you have to remember is slightly different syntax, right, when you're actually writing the code. And of course, every language has little quirks and so on, so you couldn't say, write a load of PHP, produce an abstract syntax tree, and then run it in JavaScript. It's possible, but each language has quirks in the way that things are executed and designed and so on. So whilst it's possible, you'd have to take care of a lot of weird edge cases and niche things that no one probably uses, but when you start looking into this stuff, it becomes immensely complex. So yeah, it's a fun project perhaps. But what really is kind of useful and important to your day-to-day PHP coding developer is that we can use this abstract syntax tree in the userland, that is, like when we're writing PHP, right? So why? Why would we want to do this? Well, we get a lot of insight into what's going on in our code. We can examine the structure of it. We can look at what types are of things. We can see, oh, this is a 5, this is a 6. These are integers. 1.2.3, 1.2.3, 1.23. Weird floats going on there. We can say, oh, that's a float, right? So it gives us a lot of information about our code. Well, why do we want to do that, right? Well, have a look, right? Let's look at how first, right? And then figure out, well, why are we doing this, right? For some of you, this may be obvious already, but anyway, PHP AST extension is, funnily enough, as the name suggests, an extension for PHP that gives you the AST, right? It exposes the AST to userland. I'm hoping that one day this becomes part of PHP core, just like you can do token get all. At the moment, you can't do like AST get all or whatever. The downside to this, though, is it requires an extension, and that involves installing stuff, and you have to peckle install PHP AST, which I know is not that big a deal, but It's an extra dependency, right? And maybe not everyone can install extensions as well. That's perfectly reasonable. So once the extension is installed anyway, the usage is fairly simple, right? You give it some code. That AST Dump function is it's literally just a function written in PHP that helps simplify the output because, as you've probably seen and kind of gathered by now, abstract syntax trees can get huge. So we want to format that a bit nicer. But yeah, you just call the AST parse code, give it some code as a string, and it will give you the abstract syntax tree. It's just a load of objects. You can look around it, just like you would any other kind of data structure. All right? And then there's ASTKit. It's another PHP extension. It's written by Sarah Goldman. This extension, PHP AST, was written by Nikita Popov. This one's written by Sarah Goldman. And this actually allows modification of the abstract syntax tree. Ooh, interesting. Magic things. Yeah, you can modify the abstract syntax tree and then execute it. Cool, okay. And if you're familiar with other languages, this concept is called monkeypatching, right? Which is quite cool. The downsides are it's an extension, and also, it was just a thing to muck around with and fiddle around so we can get monkeypatching in PHP. But it's not something you should be doing in production, right? Probably, maybe. Yes, but the usage is kind of similar, right? We have some code, we can execute it, right? And that actually runs the code as well. And then we can change certain values. So, in this example that's just on the README, I think, is where I grabbed this directly from. It changes the true in that statement to false. And of course, you get a different result the second time you execute it. That's what monkeypatching is, all right? Honestly, I think the API for this is very, very raw and not really that easy to understand, but it's doable. It's possible to do this, right? So there is this library written by Nikita Popov as well. It's more or less the same as the PHP AST extension, but there's one big difference. It's written in PHP, not C, all right? The upsides are it's not an extension, so you can install it with Composer install instead of Peckle install. But yeah, there is a big downside. It's much, 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 much slower, all right? Because you're parsing PHP in PHP instead of parsing PHP in C. I think I said the words in the right order then. Okay. So yeah, there's PHP Parser. But despite it being, orders of magnitude slower than doing it directly in PHP, there is big upsides to this, right? We'll get there in a sec. This is an example usage. It's pretty simple, right? You give it some code. Again, the concept's the same. You give it some code, it gives you an abstract syntax tree, right? And that gives you lots of information. And you can do lots of useful introspection, figuring out things about your code with this. So now is sort of the quick open source pitch. Don't worry, I'm not selling you anything. You can download this for free and use it. So there's this tool called Better Reflection that we wrote. Me and open source contributors and Marco. It was Marco's idea. He was like, James, write this library. Okay, then. Oh, that was dumb. And like all of those things, it takes way much longer than you expected. Anyway, Better Reflection is, funnily enough, the reflection API. It's almost exactly the same as the PHP's internal reflection API, but it uses PHP Parser. Well, why? Well, there's a big advantage that you can load the abstract syntax tree of code that hasn't been loaded into PHP. So you can statically analyze things, right, using this PHP Parser tool, which means it's actually a little bit more flexible and a bit more powerful than PHP's internal reflection. Of course, it's slower. Yeah, admit that. It's fine, because we're not running this stuff in production, right? This is static stuff, right, before we deploy to production. Okay, so Better Reflection works like this, right? We've got Reflector, that's basically the public API. We'll have a look at that in just a moment. A source locator, well, because we have to find where source code is in order to load it. PHP does this automatically, right? And you have your autoloader and stuff like that. But of course, with better reflection, we're loading code that hasn't been loaded yet. So we need to tell better reflection how to load that. So that's what a source locator is. And then you have PHP Parser, which is, of course, Nikita's library for parsing the code. And then we return the reflection itself. And then we can do like our get name and things like that, right? Do all of our normal reflection things, or most of them at least. So in the core reflection API, we've tried to keep it kind of similar. You do new reflection class, for example. If you've ever used reflection, this is probably quite familiar to you. So in better reflection, it's just slightly different. We're just using some default values here. So we've got this source locator, which sort of piggybacks the autoloader and tries to intercept calls to autoload things, which is kind of fun. That's a whole talk in itself, probably. But yeah. So the class Reflector, as I said, it's sort of made up of these source locators. We've got the PHP internal source locator. That's for stuff that is in PHP itself, as the name hopefully suggests. Hopefully we've named that well. And it's basically just a huge load of stubs, which is completely unmaintainable. But there's no reasonable way of doing it, unfortunately. There is also the eval source locator, right? But no one evals code, right? I hope. But it's there just in case you do. And then that autoload source locator. So yeah, those are the instructions on how to find your source code. If you have weird requirements or you want to load code from a string, there's other source locators you can use. All right? So the source code is then fed into PHP Parser, the AST is returned, and so on. And yeah, that's pretty much how that works. So, given a class structure, fairly simple class, I think. It's got a property and a method. We can get the AST, and we can find out information about that, right? We can find out the types of properties. We can find out the attributes of them. The method, we know what types it receives and gives back and things like that. Or the statements inside it as well. Any kind of metadata about it. Well, what lines does this method cover? So, okay, what can I use better reflection for? Well, everything you use normal reflection for, but if that's all you want to do, then it's just use PHP's reflection, right? So it's kind of a niche tool. But it means you can reflect on classes that in files and strings and so on without loading it. That's a really big benefit. So it doesn't use internal reflection API at all. That allows you to analyze things like doc blocks. Obviously, now we've got PHP 7. Hopefully, many of you are already using PHP 7. But if you're still stuck on PHP 5, you can analyze this. You can figure out types of stuff from doc blocks, rather, and do type inference that way. And there's this. You can use this for static analysis and things like that. And you can also do this Monkeypatching thing that I mentioned, right? You can modify stuff. Let's have a look at how that works. All right. So you've got a class called MyClass, for example. Very original. It's very simple. It returns the number 5. I think that's fairly clear. So we can reflect on the class. If it can be autoloaded, we can just use the better reflection standard stuff. In this example, I'm actually just loading it from a single file for whatever reasons. But we have to make sure we do this before the class is loaded, right? That's kind of the important thing, because PHP can't unload classes unless you install RunKit, but don't do that, unless you're just playing around with it, perhaps, of course. But yeah, don't run RunKit in production, please. Yeah, we basically wrap it up like an autoloader that we add in as well, which means when we modify stuff, we can tell the autoloader, hey, I've got a modified version of this class. This particular configuration will cache it in a file, so it's hopefully quicker. And then we can call this method that is not in PHP's own reflection API, like SetBody from closure. And you can give it a function. And there also exists SetBody from string, SetBody from AST, and so on. It uses the PHP Parser AST nodes, funnily enough. And we can override the method content with our own method. In this case, 4. So then when we come and execute this, the autoloader kicks in, it loads our modified version of the code, and it returns 4 instead of 5. Not what you expected. and your tests will probably fail if you've written tests, which you have, right? So would you use this in production? I hope not. There's perhaps something going wrong if you have to do this, but it's academically possible, right? Yes. So anyway, to summarize, because I think we're just out of time, for the PHP engine, the abstract syntax tree is a very efficient data structure. It's much nicer. It means you can do that compilation step faster. And it means that the PHP internal code is just that slightly little bit more maintainable. So, dive in, have a look. Concepts like AST can be used in userland. And the big benefits here is things like figuring out your types. You can do reflection on the not yet loaded files with better reflection and so on. You can do monkeypatching if you should so desire. But the biggest benefit, I think, is the static analysis opportunities, right? Looking at your types, figuring out bugs and things like that, right? There's this tool called PHP Stan. There's a tool called Execat. There's all kinds of things, and fan and so on. And these tools will allow you to find bugs in your code, right? We like finding bugs and fixing them, right? Well, hopefully fixing them. And then there's also infection PHP, which is a mutation testing tool, but I think there's a session about that later, so I won't go into too much detail there. Is that right? Yeah, okay. All right, I don't know if I've got any time for questions. Is there any time for questions? Yes? Okay, we've got time for questions. Does anyone have any questions? It's okay if you don't. Come and talk to me, I'll be around at the conference. How about if you ask a question, I'll give you an elephant? Everyone's like, yeah! That's not a question, Andrea. Okay. Any questions? No. Oh, we have one.
So what made you decide to make the better reflection? What was the use case?
So the use case, well, it was Marco's idea. I just did the grunt
Don't
work.
blame Marco.
It was Marco's fault. He was like, James, I need to write this library. Do you want to do it? And I'm like, I've got nothing better to do. But the reasons for doing that is, do you know things like Proxy Manager? For anyone who doesn't know Proxy Manager, Proxy Manager is a library that generates proxies, which kind of extend classes and add functionality to them in various ways. Doctrine does this as well. It creates proxies which allow lazy loading and things like that. If you've never used Doctrine, this maybe doesn't mean so much to you, but hey. One of the use cases, for example, is to be able to remove final from classes. So that's like a monkeypatching useful tool there, perhaps. And also to be able to analyze code without loading it for whatever harebrained ideas Marco has, usually. But there's a few use cases for it. But it's not something you want to be running in production because it's slow. It's a things you can do in your CI pipeline with kind of tool. That help? Cool.
Yes.
I guess you get an elephant then. You already have an elephant. Oh, I'm not giving you another one. You've already got one. There's all these lovely people here who are like, I only came to the talk for an elephant. All right. Thank you very much, folks. I'm gonna.
James?
There is a question. Go on.
Yep.
Sorry.
The data source loader that you have is actually quite useful in its own right. Do you have any plans to move that into a separate repo at any point?
Ooh, that's interesting. I've never thought of that. There's potential. If people want to use it, I'm quite happy to split it out into a separate component. Yeah. Open an issue on GitHub, and I'll get to it in my spare time. And you already have an elephant as well, so. Okay. Any more questions? Okay, folks. I think it's lunchtime. If you do want an elephant, come up and grab one, seeing as if you don't already have one. Thank you, folks. Cheers. Thank you.